In this video, we're going to look at our third and final method for solving systems of equations, and that is substitution. This is going to be very similar to the second part of the elimination process, where we took that first coordinate and substituted it back in. Except now, instead of taking a number for one of the variables, we're going to find an expression and substitute that in instead. So, again, it's going to be important to read the directions because here we're asked to solve by substitution, so we want to make sure we use it. The thing that we're going to look for when we're solving by substitution is whether we can easily isolate one of the variables. So in this case, y is already isolated, and we know that y is -8. So that means I'm going to take this and substitute it in for y in the first equation. So we're going to say -6x plus 5 times -8 equals -22. And now in doing so, I've gotten rid of one of the variables, and I'm just left with a one-variable equation that I can very easily solve. So we continue to do so. We have -6x minus 40 equals -22, and we just continue to solve this out, and we end up with x equals 3. And in this one, it's super easy because we were already told that y equals 8, so we can jump right to our solution, which is going to be 3, -8, and this is a consistent and independent system. If we look at our second system, this is a little different because both equations are solved for y. So if we think back to our reflexive property, we know that y is equal to itself. So I'm allowed to say that. Then by the substitution property, I can take this first expression for y, substitute it on one side, and take my second expression for y, and substitute it in on the other side. So now I can create the equation 4x minus 19 equals -2x minus 1, and I've completely eliminated y from the equation by substituting in those two expressions. Now I have just a simple equation with variables on both sides, but only one variable, so I can go ahead and solve this. Pause the video, see if you can solve for x, and then find the value for y, and in doing so find the solution to this system. Alright, so for this system, when we solve that first equation, we end up getting an x value of 3. Then I can substitute this x coordinate into either of the equations, and regardless of which one I substitute into, I'm going to get a y coordinate of -7. So my solution is going to be the point 3, -7. If I graphed both these lines in the coordinate plane, this is the point where they would intersect. So we have a consistent, independent system. This is where it gets a little more complicated because instead of substituting in a single value or setting two expressions equal to each other, this is where we have to actually substitute an expression in. If I look at my system on the left, this one's already solved for y, so I already have that expression I'm going to substitute in. On the right-hand side, neither of my equations are solved for y or for x, so I'm going to have to do a little bit of maneuvering to get a variable isolated before I can do any substituting. So if we look at the first example here, I know that y is equal to 4x minus 3. That means that anywhere I see a y in my second equation, I can take 4x minus 3 and substitute it in. Remember that whenever we substitute, we want to use parentheses, because this is 2x minus y, not 2x minus 4x minus 3. Because when we're subtracting that -3, it's actually going to become positive, so we just want to be really careful with the signs. So we have 2x minus 4x plus 3 equals 1. Anytime you're using substitution, you must show this first substitution step. Your work will not be considered complete unless you have this step here. So we go through, we simplify, so we have -2x plus 3 equals 1, and we're going to end up with an x coordinate of 1. Now we can go ahead and substitute this into either equation. Again, it doesn't matter which one we pick, and we can use our first one if we want. So y equals 4 times 1 minus 3, and we're going to get a y coordinate of 1. So we have that one solution, which is 1, 1, and this is a consistent, independent system. Go ahead and pause the video, see if you can isolate one of your variables in the top equation, and then use substitution to solve the system. Alright, so I solved the first equation for x. You could also solve it for y if you wanted to. But either way, we're going to take that expression and substitute it into the second equation. When you're substituting, you never want to substitute an expression back into the equation that it came from, because then you're just going to end up with all real numbers, because it'll always work. So we always want to substitute back into the second equation. So there we get a y value of 0. Substitute that into either equation. We get an x value of 5, which means our solution is going to be the order pair 5, 0, which means we have a consistent, independent system. Go ahead, pause the video, see if you can solve the system on the left on this page. Alright, so our first equation is already solved for y, so we can substitute that into the y in the second equation. When we do that, our x terms end up eliminating themselves, and we end up with the statement 10 equals 8, which is a contradiction. So this is no solution, and we end up with an inconsistent system. Go ahead, pause the video, see if you can solve the last one here. Alright, if we solve the second equation for x, and again, you can solve any equation for any variable, you just want to make your life as easy as possible, so look for the simplest one. We substitute that back into the first equation. We end up with the statement 16 equals 16, which we know is a true statement. So this is going to be our infinitely many solutions, which means we have a consistent, dependent system.